Hello, this is Naz from NB Network Lessons. Hope everyone's doing okay and in high spirits. My today's topic of discussion is sequences in advanced calculus, and this is lesson number 70. So first of all, thank you for joining everyone. I really appreciate it. And having said that, let me go ahead and dive in. What are sequences in advanced calculus? So sequences are basically a list of numbers. It's really nothing but just a list of numbers. For example, you can have C1, C2, C3, and it just goes on and on and on, right? It's just a list of number. Just a list of numbers. So that's what really it is, okay? Now, what we can do is we can identify sequence, or we can list sequence in terms of n, okay? We can say n terms, or we can say n elements. Let's see how. So let's say you have something like this. You have to represent a sequence number in curly braces. So something like this. So you have ace of n, okay, curly braces, okay, or basically this is really represented like this. Ace of n, you have limit going up to infinity and starting n is equal to 1, okay? If you see something like this, it's understood that n is equal to, its limit is n is equal to 1 and go on up to infinity. So keep that in mind. Let's look at an example. So if we look at an example, what we will see is, let's say you have ace of n is equal to 4 times n, okay? Whereas we say n is equal to 1 going up till infinity. All right, easy peasy. So if I do n is equal to 1, okay, I get 4. If I do n is equal to 2, I get 8. If I do n is equal to 3, I get 12. If I do n is equal to 4, I get 16, and so forth, right? So then what I can do is, I can say, I can represent this in curly braces like this. I can say 4, 8, 12, 16, goes up to ace of n, okay? And this is all represented in curly braces. So this 4 is when n was equal to 1. This 8 is when n is equal to 2. This 12 is equal to when n is equal to 3, and so forth, right? So let's draw a graph. Let's draw a graph for that. So if I draw a graph of that, and I have y-axis and I have x-axis. On y-axis I have a n, and on x-axis I have n. So let's see if we can draw this. So when n is equal to 1, okay, ace of n is 4. When n is equal to 2, ace of 4 is equal to 8, which is right here, okay? And when n is equal to 3, we have ace of n 12, all right? So if we draw a graph, that graph is going to look like this. It's going to be like a straight line, okay? And this straight line goes up to infinity. So that's the graphical representation of that. Now, let's look at another example. All right, let's see if we have, we say ace of n is equal to n over n plus 1, okay? So let's see if we can represent that in form of a sequence. So I go draw a tilde bracket. When n is equal to 1, this is going to be 1 over 2, right? When n is equal to 2, this is going to be 2 over 3. When n is equal to 3, this is going to be 3 over 4. When n is equal to 4, this is going to be 4 over 5. And if I keep on doing that, you know, this goes up to infinity, but let's say if I stop at 700. So 700 is the numerator. What is going to be the denominator? 701. So basically the point I'm trying to make is that the difference between numerator and denominator is always 1 in every element. And you see that right here, right? So what does that mean? This difference is 1. So what that means is that if I draw a graph of this right here, I have an, it's almost like a function. It's not really a function, but I mean, it looks like a function. And then you have n right here, okay? If I draw a graph, I know my ace of n is gonna be, the difference right here is 1, right? So let's say if I draw a straight line right here. There we go, okay? Now, if you start plotting n is equal to 1, if n is equal to 1, what is the function? It's half. All right, when n is equal to 2, it goes up to 2 over 3. When n is equal to 3, it goes up to 3 over 4. When n is equal to 4, it goes up to 4 over 5. So the point I'm trying to make is that this right here, your function is going to look like something like this. It's going to go like this, and it's almost converging. It never really touches the line 1 because there is a difference, but it almost converges, okay? So then, you know, for simplicity, since the difference is so low, we can say, yeah, it converges almost at 1, okay? So I just wanted to share that information with you. Let's see, we do another problem, okay? So let's see if we look at another example. So what we do is that we have a problem which says ace of n is equal to n over 2n plus 1. And you've been asked to find the elements or the terms. So put the curly bracket right here. When n is equal to 1, this is going to be 1 over 3, right? So actually, yeah, n is equal to 1, 2, 1, 2 plus 1, 1 over 3. When n is equal to 2, it's going to be 2 over 5. When n is equal to 3, it's going to be 3 over 7. When n is equal to 4, this is going to be 4 over 9, all right? And when n is equal to, let's say, 5, this is going to be 5 over 11, okay? So this is your answer right here. Because what we are seeing in this particular case is n is equal to, limit in this one is n is equal to 1 approaching 5. So that is your answer right there. Let's look at another problem. So we have, let's say, an is equal to 1 over 2n. How would you solve that? Well, same philosophy. You know, put n is equal to 1. This is going to be 1 over 2. Put n is equal to 2. This is going to be 1 over 4. Put n is equal to 3. This is going to be 1 over 8. All right. Put n is equal to 4. This is going to be 1 over 16. So this is my answer because I've been asked limit from n is equal to 1 approaching 4. All right. So that's all I wanted to share in this particular lecture. I'll come back and share some more examples with you. Till then, take care of yourself. And if you like the contents, please go ahead and give me a like. Thank you so much. Bye-bye.